fourth lecture on Legendre differential equation. In the earlier lecture, we have discussed Rodrigues formula. In Rodrigues formula, one gets the special function of a given order by differentiating successively a known function. And at the end of the last class, we have expanded this one and written this in convergent binomial series and written it explicit in a compact form like this. And we promised that today we shall discuss generating function. The generating function of a special function like Legendre or Hermite, Bessel, Logger, etc., or there are others too, is a function involving an argument and a parameter. Say g is the generating function, then g is the x is the argument and t is the parameter. If we call, well, this is PL of x, so this is the argument and there is a parameter t. And the expression for generating function can be expanded as an infinite series in powers of parameter. And if we expand and the coefficient of t to the power k is related to the special function of order k. It is related to the kth order special function. This is the spirit of generating function. This technique is very much helpful if one wants to calculate higher order of the special function. As we have seen, the Rodrigues formula or the series expansion, they are for Legendre polynomial, they are suitable when the order L is small. For large L, neither these formula are applicable, are suitable, not applicable, I must say suitable. And for getting special function of higher order, it is the generating function which is of great use. Now let me come to the generating function of Legendre polynomial. We consider the function g of xt is equal to 1 minus twice xt plus t squared to the power minus half, where the restriction is that mod x is less than or equal to 1 and t is less than 1. Oh, sorry. This is the restriction. We rewrite this as 1 minus z to the power minus half, where z is equal to 2xt minus t squared, taken t common, 2x minus t. If we expand this in binomial series, we write it as k is equal to 0 to infinity 2k factorial 2 to the power 2k k factorial square and z to the power k. We use this expansion, and for z we write this. So this is summation over sum over k 2 to the power k factorial 2 to the power 2k k factorial square times t to the power k 2x minus t to the power k. Note that k is an integer, so we can expand it in binomial series having finite number of terms. So we rewrite it as for this expansion. kcn t to the power n 2x to the power k minus n. So this is the expansion. This part is written instead of this one. So this is binomial expansion. We know it. Then we combine this. Say k is an infinite sum and n is a finite sum. Now we have 1 to the power minus 1 to the power n. This is 2k factorial, 2 to the power 2k, k factorial square. Then coming to this part, this is k factorial, n factorial, k minus n factorial for nck, and t to the power k plus m, e to the power k minus n, x to the power k minus n. Now this factorial k cancels with this, so we write it like this. If we adjust this one, 1k power goes, and this is 2 to the power k minus n. Then we have k factorial, n factorial, k factorial, n factorial, k minus n factorial, t to the power, this is k plus n, t to the power k plus n, and x to the power k minus n. We now make a change. The n sum remain, we do not do anything with n sum, rather we introduce an L quantity, L, which is k minus n. So L is a infinite sum is taken over L, so this quantity becomes summation over ln minus 1 to the power n, minus 1 to the power n, this part, then 2k, so this gives you k is equal to L minus n, so this part is 2L minus 2n factorial. Then k minus n is k minus n is equal to L minus n, that is L minus 2n. I have done a mistake. Consider the simplification of this 2 to the power k minus n on the numerator and 2 to the power 2k on the denominator. So this is 1 upon 2 to the power k plus n. I have written it as minus n. So this is 2 to the power simply L. K factorial means L minus n factorial, n factorial, and k minus n is L minus 2n factorial, and then t to the power n, t to the power L, and 2x to the power x to the power L minus 2n. So this is the simplified version. Now we rewrite it as summation over L is equal to 0 to infinity. Then we have t to the power L, then sum over n is equal to 0 to upper limit. I will write it a bit later. Actually, if we come from here, the n sum ranges from 0 to L, 0 to k, sorry, it is 0 to k, then it should be an infinite sum, but there will be some restriction. Let me write it first. N factorial n minus L factorial, sorry, L minus n factorial, L minus n factorial, L minus 2n factorial. In the numerator we have 2L minus 2n factorial x to the power L minus 2n. This sum is up to k, that means k plus n is equal to L, that is k is equal to L minus n. So this sum is actually up to L minus n, but there is restriction. When n value is such that n minus 2 L minus 2n must be greater than or less than or equal to 0. Sorry, this must be greater than or equal to 0. So there is a restriction on 2n value. So this sum is actually extends up to capital N, and this quantity within is nothing but PL. So we write it as sum over L is equal to 0 to infinity t to the power L PL of x. This is the generating function for Legendre polynomial. To show its utility, let me use this function, and we use this expansion for few low order terms. So we know that this is equal to sum over L is equal to 0 to infinity t to the power L PL of x is this. Now this expansion is 1 plus half z plus half into 3 by 2 by factorial to z square and so on and so forth. This is that. If we replace z by the in terms of x and t, it is 1 plus half z is equal to this t into 2x minus t plus this is 3 by 8 z square means t square 2x minus t whole square. This is 15 in the numerator 15, and in the denominator it is factorial 3 means 6, and this is 8. So 6 into 8 48. This term 3t square by 8, and we have 4x square minus 4xt plus t square. Coming to this term 15t cube 48 8x cube minus 12x square t plus 3 into 2 6xt square minus t cube plus higher order terms. You see the term that will come from the next term will have lowest power of t as t to the power 4, because there will be a multiplication by t to the power 4. So this is correct up to t to the t cube. This expression is correct or complete, we shall say complete, up to t to the power cube. So we can expand, collect the coefficient up to t to the power cube from here. T0, taking T0 times, there is single term which is independent of T0. So this t to the power 1 into the t to the power 1 term will come from this. So this is t and this is x. This may create confusion, so we write it like this. There is no other term which is t, which is the coefficient of t. Now coming to t square, there are two contributions. One is this is minus half from this term, and there is another contribution to t square is this. This is plus 3 by 2 x square. This is the contribution of. Now coming to t cube. There is a contribution to t cube. So this is in the denominator half, because it's multiplied by 4. So with minus sign, 3 by 2 x. This is this term. And there is one other contribution to t cube is from this. So this is 15 in the numerator and this is 6. So this is 15 into 8 by 48. Sorry, 5. So this is 5 by 2. The coefficient is x cube. And if we collect the coefficient of t to the power 4, it will be an erroneous one, because there will be one contribution from t to the power 4 from the first term. That is the term coming from 2x minus t to the power 4. The leading term will be 16x to the power 4 multiplied by a factor that will contribute to t to the power 4. So we are not going to collect the coefficient of t to the power 4. Let me first rearrange the term. This is t0p into 1 plus t1 into x plus, if we take t square and take half common, then this is 3x square minus 1. Then again this is t cube, and if we take half common, this is 5x cube minus 3x. As for generating function, this is t0 p0 of x plus t1 p1 of x plus t2 . So if we collect the coefficient, then we find that p0 of x is equal to 1, p1 of x is simply x, p2 of x, here the coefficient is this, 3x square minus 1 by 2, p3 of x is equal to this much, if we put x is equal to 1, you see this is 1, this is 1. So This formula can be applied to get Legendre polynomial of higher orders. One more thing, note that P1, P0 is even, P2 is even, P1 is odd, P3 is odd. So they are even, this is odd, this is odd. So Legendre polynomial of even order is an even polynomial, and Legendre polynomial of an odd order is an odd polynomial. This is the beauty of generating function. We can get the special function of higher order from this. The generating function is also useful in getting the recurrence relation. Earlier we have obtained recurrence relation in terms of the coefficient ck, which is used in the expansion of power series. There are another recurrence relation that connects the Legendre polynomial of a given order to its neighboring order. They consider the generating function g of xt is equal to 1 minus 2xt plus t square to the power minus half is equal to summation over L is equal to 0 to infinity t to the power L PL of x. This is the generating function. We may differentiate it partially with respect to t. So we differentiate it partially with respect to t. So we get del g del t is equal to minus half 1 minus 2xt plus t square to the power minus 3 by 2, then minus 2x. We are differentiating with respect to t, so this will be differentiated L t to the power L minus 1 PL of x, L is equal to 0 to infinity. We rewrite this one as, if we take minus 2 common, this will become x minus t, and this minus 2 will be adjusted over here. So we write it as x minus t, and t to the power minus 3 by 2 we write it as 1 minus 2xt plus t square to the power minus half 1 minus 2xt plus t square L t to the power L minus 1 PL of x. Now we multiply this with this, and for this we use another generating function, or we can write x minus t summation over k is equal to 0 to infinity t to the power k pk of x is equal to 1 minus 2xt plus t square summation over L t to the power L minus 1 PL of x. This is an identity in T. The coefficient of t to the power n gives t to the power n. So when we multiply, this term will contribute to t to the power n for k is equal to n. So this is k pn of x. This is the first term. This is t to the power k plus 1. So this will contribute to t to the power n when k plus 1 is equal to n, that is k is equal to n minus 1. So this is minus n minus 1 of x. Now coming to the right hand side. Here the if we multiply this with this, so this will contribute to n when, that is when L is equal to n plus 1. So this is L is equal to n plus 1. So this is n plus 1 p of n plus 1 of x. Now coming to second term. Second term, if we multiply it by t with this, it is t to the power l, and it will contribute to xp t to the power n when l is equal to n. So this is minus 2x npn of x. Now coming to the next term, it is the coefficient of t to the power l plus 1. When l plus 1 is equal to n, that is l is equal to n minus 1. L is equal to n minus 1. So we have plus n minus 1 p n minus 1 of x. Now p n minus 1 is in two, it occurs in two occasions. Pn occurs in two occasions, and we write n plus 1 pn plus 1 of x. So we give it one side and take the others on the other side. So if we take it on the other side, this will be 2n plus 1 x pn of x. We have considered this when it is taken on the other side, it is for plus sign, taking x common, so 2n plus 1x. And this is minus term, this is minus term, and when this is n p n minus 1 of x. This is the first basic recurrence relation that is obtained by differentiating the generating function partially with respect to the parameter. So this is one of the fundamental recurrence relation, and let me apply this for the calculation of Legendre polynomial of higher order. So we write this expression p n plus 1 of x is equal to 1 by n plus 1 2n plus 1 of x pn of x minus n pn minus 1 of x. We start with the value that p0 of x, I am not writing the arguments, p0 of x is 1 and p1 of x is x. So if we put n is equal to 2, n is equal to 1, we get for n is equal to 1, we get p2 is equal to n is equal to 1, so 3x p1 minus 1, n is 1, p0. So this is p1 is x, so this is half into 3x square minus 1. With this p2 we come to n is equal to 2. For n is equal to 2, this is p3 is equal to 1 by 3. Then we put n n is equal to 2, so this is 5 x p2 minus 2 p1, so 1 by 3, this is 5, and p2 is 5 by 2 x into 3x square minus 1, and then this is minus 2x. On simplification, x cube, this is 5 by 2 x cube, 5 by 2 x cube, and coming to x term, this is 5 by 6, this is 5 by 2x minus 2x, so this is 2 taken common, so this is 5 minus 4, this is I've done some wrong. Let me check. N is equal to 2, this is 1 by 3, this is 5x p2, and n is equal to 2, so this is 2p1, so it's okay. X2p for p2 we write this one and p. Now coming to the coefficient of x, this is 15 by 2, sorry, this is 15 by 2, 5 and 3 by this is 5 minus 5 by 2, and then we have minus 2, so this is taken 2 minus and 2 common, so this is 5 plus 4 is equal to minus 9 by 2, and when it is multiplied by 1 by 3, this becomes minus 3 by 2. So this comes out to be taken half common, 5x cubed minus 3x, which we obtained earlier. So there is another way of getting this recurrence relation. Higher order Legendre polynomial can be generated starting from the knowledge of P0 and P1. There is another generating function. Before going to the second one, students are advised to find P4, P5 and P6 using generating function, recurrence relation. Now this generating function is a function of argument x and parameter t. This is a function of argument x and parameter t. In the earlier occasion, we have differentiated the generating function partially with respect to parameter t and obtained the recurrence relation involving different orders of Legendre polynomial. So now if we differentiate this expression with respect to x, we will get an expression for the derivative of the Legendre polynomial. So we differentiate it partially with respect to x, we get minus half 1 minus 2xt plus t squared to the power minus 3 by 2 and this is minus 2t, and on the right hand side we will have L is equal to 0 to infinity t to the power L PL prime of x. Now here PL prime of x means ddx of PL of x, that is the derivative of the Legendre polynomial. We rewrite it as or again this is an identity, and a coefficient of t to the power n gives here k plus 1 will be equal to n, so this is k is equal to, we will have n minus 1 of x on the left hand side. On the right hand side it will be p n prime of x, then this term. This is the second basic recurrence relation that is obtained by differentiating the generating function partially with respect to x. This gives you the value of the derivative of the Legendre polynomial in terms of the Legendre polynomial itself. These are the two basic relations which can be used suitably to find out the Legendre other recurrence relations. So this is all for today. Before concluding, I advise the students to our listener to consult books so that you can get other recurrence relation involving Legendre polynomial and their derivatives. But the basic two relation has been worked out over here. In the next class, we shall discuss the orthogonality of the Legendre polynomial.